Now we will consider what's called the power rule. And the power rule is the rule that will help us find the derivative of the family of functions just like x squared or x to the fifth or x to the negative seventh. These all belong to the family of x to the n power. And so we're going to be considering the derivative of all of these, x to the n power. Now notice in this case, the exceptions to this would be things like x to the first, because that equals x, and we already showed that its derivative is 1. That would also not include x to the 0 power, because anything to the 0 power is 1, and we've already shown that the derivative of a constant is 0, so these would be exceptions. We're dealing specifically with x to the n. What would its derivative be? So let's prove it, and there's only one way for us to prove it. We know that we're looking at the limit as h goes to 0 of f of x plus h minus f of x all over h. Now remember that our function happens to be, we're using y equals x to the n power. So when we substitute, we'll have the limit as h goes to 0 of x plus h to the n minus x to the n over h. And you might be thinking to yourself, how in the world are we going to unpackage this? We will need to use a little factoring ingenuity here. Something to notice. You know that x squared minus y squared equals x minus y times x plus y. And you ought to know, although you might not, that x cubed minus y cubed equals x minus y times x squared plus xy plus y squared. Furthermore, you most likely don't know, but hopefully you'll start to see the pattern. X to the fourth minus y to the fourth is equal to x minus y times, notice the pattern, x cubed plus x squared y plus xy squared plus y cubed. If you don't see the pattern, notice in the x, the power of the exponents for x goes 3, 2, 1, and then 0. And notice the power in the y's goes 0, 1, 2, and 3. And this is true in all cases where the powers are positive at any rate. So one thing that's true about our proof is that we're actually only proving it for positive exponents right now. But nevertheless, this is helpful because using that pattern below, this numerator factors for us. And it will factor into x plus h minus x times, and if you notice the pattern, then this should make sense to you. This will be x plus h the n minus 1 plus x plus h to the n minus 2 times x plus, and it's just going to keep going for a while, and eventually it'll work itself out to being x plus h times x to the n minus 2 plus x to the n minus 1. Right, just using some factoring facts. And all of this is divided by h. But the cool thing is what happens right here. Because notice that x plus h minus x equals h. And that h will divide out with this denominator. So we're left with the limit as h goes to 0 of this kind of nasty looking thing, x plus h to the all to the n minus 1 plus x plus h to the n minus 2 times x and then that's going to keep going for a while. And we'll have x plus h times x to the n minus 2 plus x to the n minus 1. And again, our algebra becomes the issue here. Notice that since we can take the limit now, and when h is 0, everywhere there's an h, this is going to go down to just x. So we'll have x to the n minus 1 plus x to the n minus 2 times x plus, and it's going to follow that pattern the whole way. And this will be x to the n minus 2 times x plus x to the n minus 1. And notice, just using your algebra skills, that this will become x to the n minus 1 because the bases are the same, they're both x. I'm multiplying, so I can add those exponents, and minus 2 plus 1 is n minus 1. And that's going to happen in every term in this sequence. I'm just going to have a bunch of n minus 1s. In fact, there will be n of them. So this is going to simplify down into n times x to the n minus 1. And this is the full proof for just positive exponents, but it is always true that given f of x equals x to the n, its derivative will equal n times x to the n minus 1. And this can be really confusing, but we've now proved it. Let's look at some examples. So let's start with just x squared, which we've seen a lot of. So if y equals x squared, what's its derivative? Well, by the power rule, in this case n is 2. By the power rule, all that means is I'm going to drop the exponent out front, so y prime would be 2 times x, and now I have to subtract the power by 1. X to the first, so y prime is 2x. If I was looking at example 2, f of x equals x to the 6th, by the power rule, f prime of x, bring the exponent out front, so this will be 6 times x, subtract 1 from the exponent to the 5th, and I'm done. Let's look at s of t equals t to the 30th. Again, by the power rule, I'm going to bring the exponent out front, so this will be 30 times t Subtract 1 from the exponent to the 29th. Let's look at the next example. Y equals root x. And that looks, if you just remember that the square root of x is the same as x to the 1/2, then the power rule comes into play. Y prime, bring the exponent out front, so it would be 1/2 times x. Subtract 1 from the exponent. 1/2 minus 1 is negative 1/2. If I was dealing with y equals 1 over x, I just need to realize that this is the same as x to the negative 1 power. So then y prime, bring the exponent out front, and subtract the exponent by 1. Negative 1 to the times x to the negative 2. And I could rewrite that as negative 1 over x squared. Let's do the last three, since we're here. So we've got f of x equals 1 over x cubed. And to use the power rule, I need to rewrite this as x to the negative 3 power. So, f prime of x, bring the power out front, subtracted by 1. And I could rewrite this as negative 3 over x squared. If I do example G, s of t equals 1 over the cube root of t. And I need to remember that that's the same as t to the negative 1/3 power. So, by the power rule, I'll bring the exponent out front, so it'll be negative 1/3 times t. Subtract the exponent by 1, so negative 1/3 minus 1 is negative 4/3. And if I wanted to clean this up, I could. This is the same thing as negative 1 over 3 times the cube root of t to the 4th. Although you don't have to do that. Last one, y equals 1 over x to the 3/4. I just need to recognize that that's the same thing as x to the negative 3/4. So by the power rule, y prime equals, bring the exponent out front, times x, subtract the exponent by 1, negative 3/4 minus 1 is negative 7/4. And I found all of these derivatives by using the power rule.